In this last demo on the forcing, we're going to learn how to create our own forcing extraction function to access any data set that you want. You know, so far we did the NSEP reanalysis, but suppose that, for example, you want to create an extraction function to interpolate the ecmwf data. So let's go back and look at the main NC forcing here. And in order to provide the extraction from a different data set, we can use this as a template. And if we go in the time-dependent forcing, for example, and suppose we want to extract the surface winds from the ecmwf, really all we need to have here is a function similar to this one, okay, that produces this fork D, which is the extraction from a particular data set. Now, to give an idea of how this function should look like, let's go again in NC files. Let's fire MATLAB. And let's look at the structure of a simple fork D array here, like this one. And I'm just gonna, run this function here. Actually, let me just do it by hand here. So, for example, this would be my date. Let's just put date num of, say, 2001, 1, 1st of January, and say the month, the daily value, okay. And what else do I need to, and then the type of variables vars. In this case, I want only the SUSTR, okay. And the grid array, let's load a grid here. For example, we were working, I believe, with the N Pacific. Okay, so then we do that, and is extracting that particular variable here. Okay, so if I do fork D, I have here, a simple fork D, which is that portion of the winds, over that cover the grid that are of interest. So we have to basically create an array similar to this, but for the ecmwf data. Okay, so let's start that, and let's close this. Actually, let's copy this as a template, and let's create something called RNC extract ecmwf, and let's just do the UV stresses for now, just to simplify our life. Okay, so we're just going to do one specific extraction function. This is going to be a function in MATLAB, function, and we'll look, the inputs will look something like this. Okay, where we pass a longitude, a latitude, and a date, of when we want to extract. And this function we said we called extract, RNC extract. So let's just replace this function call like this. So we do that. Okay. So now the next step is first to access the ecmwf data. And here on the cluster, I have the ecmwf data downloaded in a directory called era40. And here I have a directory with all the netcdf files of the monthly averages. Okay. And so what I want to do now is I want to create a CTL, a control array, that loads a map of all these files so I can access the ecmwf data using my RNT toolboxes. And in fact, here what I've done, once I download these data sets, I create a MATLAB or toolbox for this particular data set. And in this MATLAB toolbox, I have a function called ecmwf load monthly CTL, which basically creates such a CTL, which is a concatenation of all those files that we've just seen. So let's add this in our MATLAB function here. So the first thing I'm going to do is CTL equals, I'm going to load the CTL of the monthly, so I have access to the data. And in order to do that, I have to add, for example, I have to add this directory in my MATLAB path, which is the directory of this additional toolbox here. So I'm going to do that. Ints add path F12. Okay. So now I can execute, for example, this particular, I'm going to try it whether it works into a MATLAB window here. So I'm going to clear everything. I'm going to do F12. And now I have my CTL. Okay, and this CTL has a lot of files here, 1 to 10, for example. And let's look at one of those files, for example, file number 1. It's located here. The next thing I need to know is the name of the wind stresses, and I can do that simply by doing ncdump of this particular file, and then I'm going to grep minus I, the string stress, and then I'm going to do a more. And if I do that, I see that there are some variable names like EWSS, which is the east-west surface stress, and NSSS, which is the north-south wind stress. So these are the two variables that I need. You see there's a lot more variables in this file. In fact, if I just look at all the files, the ecmwf data has tons of different variables that go from snow evaporation, you name it. Okay, so, but we're only interested in the wind stresses for now. So we can go back to our edit here, and we're going to, select these particular files. Now the next thing, so now that I know the name variables, what I need to do is I have to create, I have to load the grid on which these variables are defined. And so let's look at the grid information. And for example, if we look in one of these files here, well, actually, let's go back here. Let's MATLAB. Let's see if we have some information. So we have a longitude and a latitude here, which are contained in this thing. So I just have to load them. Okay, so it's longitude and latitude. That's how they're called. So I'm going to go here in my MATLAB, edit, and I'm going to say, okay, NC. I'm going to open one of these files, because since all of them contain, this information, CTL file, say 1. Okay, and then I'm going to say lon equals NC of longitude. Okay, I'm going to load all of it, and then I'm going to also YP latitude. And I'm going to do that, latitude. I'm going to try whether this works by just executing this on the MATLAB command. So we'll do that, and so now I have longitudes and latitudes. Okay. Now the longitudes follow the convention 0 to 360. I like to use the opposite convention. So in my little script here, I'm going to say that longitude here is minus 360. So I put them in the other convention because I like it. And at this point, I'm going to produce a mesh grid of these. Lon equals mesh grid of lat, comma lon. Okay, so I have that. And I'm just going to redo this again, making sure that it works. I do that. Size of lon. That's very good. And now I'm going to try actually to load, for example, a particular array. So I'm going to say, for example, SUSTR equals RNT underscore load var of CTL, comma, let's load one of them just to test whether this is working. And the name, for example, of the U component of the stress is the east-west, so it's this name over here, EWSS. Okay, and so I do that. And I'm going to load it and just make sure that it's properly loading. Size of SUSTR. It seems like it's loading. I can do now a figure of this. And I'm going to RNT. No, actually, in this case, I don't have a grid for that yet, so I'm just going to have to plot it by doing this. And what you see is that that it has the whole globe, and so the next step is, of course, we only want winds over the ocean, so we have to figure out also the mask associated with this NCEP stuff. And so once again, the way to see that is to look in the forcing file and see if there's any information about the land mask. And so let's do grep minus I of mask more. And there is no mask information in this particular case. So how do we go about that is very interesting. So let's see if we can find some other way of getting the mask information. Now, one thing we could do, we could figure out if there's variables that are only defined over the ocean, and we can see what we have here. Sea ice cover, ice surface. Let's see if there's a variable that we can use for the masking that would contain some masking. Snow evaporation, these are all like atmospheric variables. It's going to be difficult, perhaps. Mean sea level pressure, U, winds, total cloud cover. These are other atmospheric variables. Atmospheric variables, atmospheric variables. This is still atmospheric variables. Atmospheric variables. Runoff. This is going to be hard. And so we really don't have a mask here, which is not very good. And therefore, we have to resort to other ways of figuring out what is the mask of the NCEP of the ERA 40. And I think the mask is probably contained in this file. Actually, you see I created this array called mask. So we're going to load that. See, I was smart enough when I was working with this. So I did find the mask on the web or from the dataset, and I saved it in this file here. So I'm just going to load it. And in MATLAB, load F12. And it is saying that it cannot read. File does not exist. Why is that? Maybe I'm in the wrong directory. Yes, it's actually in one directory up. It's in this directory here. Okay, so let's take that, MATLAB. Okay, whose? And here now we find in fact that there is a mask, and so we can now p-color that times the mask. And let's see how this looks like. And now we have a mask, and it looks very nice. You could see that shading flat. Now you can clearly see, for example, these winds, along the Antarctic cyclone polar current. And these winds, as you can see, are this is the zonal winds, and you can see that these are actually defined as positive, so they're going in this direction over here. And here you have some kind of information of trade winds in the negative direction. So great. So we have the mask. So we're going to add this command here into our edit window. So an additional thing that we need here is to load the mask. So we do that. Okay. So the next thing is we want to find the subgrid that is relative to the North Pacific. Okay. So what we're going to do is we're going to steal a part of code from the previous extracting routine that finds the grid. And so I'm going to stop here. I'm done here. I'm going to go into MATLAB here and more. It's called RNC extract underscore. What is it called? NCEP. NCEP. No, we actually wanted the extract. Which one are we working on? Okay, NCEP. I think any of these will probably do fine, actually. So let's just do a type of this extraction routine. And if we go at the beginning here, we find that there is a place where we select the lon min and lan max of these things. Okay, and this is where we do it. Okay, so we go back into our edit window. So now is select the ij indices of the subregion of interest, and we can paste this here. And so the first thing I find the lon min of this array, the lon max, the lat min, the lat max. This is of the input longitude and latitudes, and then in here I find the ij's on the lon grid that are relative to that. Okay, so for example, in this particular case, let's load a grid here to produce this example. So we're going to see GRD equal MT grid load of N Pacific, and then we're going to say ln r equals GRD dot ln r, and let r equals GRD dot let r. Okay, so now we can go and test this here. This would be, I'm faking the argument, input argument of this function so that I can test it as I'm writing it. So this would be the longitude and minimum latitudes for the subgrid, and I'm going to find where this grid is reside inside the ecmwf data. So I'm just going to execute that, and now I get a range of ij's indices. So that means that now if I go back into my window here, I can actually go here and do rnt load var ins seg p, and then I just need to take the I and j and then the surface value of that. So this would be the u and then the v component. Okay, and the v component is called ns. Okay, and then the mask, I'm going to readjust the mask to be mask r, let's call it, and it's going to be mask of only ij's locations. Okay, so let me save that in the meantime, and let's execute this extraction. I'm still extracting one value, but this is later we're going to extract the time values that we want. And now we can p-color just this portion of the grid, which would be ij, and in this case su, scr, that's fine, and mask r. Okay, let's actually open another figure here so we can look at it. And now you can see that very clearly that the only place where we have the data is on the North Pacific grid, and we can also hold on world coast. And so now we've extracted ecmwf data only for the North Pacific grid. Okay, so that's very good. The next thing to do is to look, for example, this CTL array. And you see that the CTL, in this case, the way I produce the CTL, has a date num. Okay, and let's check whether this date num is in good shape by doing this. And you can see that, in fact, this is working very well, and it has all the values starting from 1957. These are monthly averages since 19. So this is very good. So what I'm going to do now is I'm going to select the time that I want, and the time is input in this myDate array here. And so because these are monthly values, the first thing I'm going to do is I'm going to go here, and I'm going to say myDate, okay, is going to I'm going to convert this into years and months, so I know exactly what stuff I want. And so this is going to be let's see, dates. This is a function here that I'm going to use to convert that into years and months, myDate. Okay, so that's that. And once I have that, I'm going to do for I t equals 1 to length of myDate. I'm going to find all the records of the ecmwf that match the dates. I'm going to find en equals find where year of it, of the particular record that I'm looking at, is equal to ctl.year, and month of the particular record is equal to ctl.month. Okay, and then I'm going to say here that my indices of, say, k is equal to in of 1. Okay, so I'm just producing now, and here I have to say that k equals 0, and here every time I find an index I say k equals k plus 1, and I just assign that index there. Okay, so I can let's say that my date is equal to my date is going to be equal to, say, date num of 2001, 1, or in this case the 15th of the month. Okay, since we're working, so that's the value. If I now test this with this particular function here, we're just going to test this and see, oops, if this will work. First we have to convert it into years and months. Then we go here, we press it, and this function indices now should have the index associated with the right date, which was 2001, January 2001. And if I do ctl.datenum of 522, and I look at the date string of that, date str, in fact, I find that it's the 16th of January of 2001, and in this case, I'm only searching for the month. I'm not searching for the specific day of the month because these are already monthly averages. So this works. So at this point, this, of course, my date could be a longer array. It doesn't matter here. This is very general. So then here, we're just going to load, this particular index. So we're going to go say ints, and we're going to look indices, the one that we want. Okay. And then we're going to do the same here. Oh, oops, undo. Ask undo. We're going to put this one to indices. Okay, so that's done. That's very good. And at this point, actually, these things we can actually start adding into the fork D array, except that there's one thing that these guys actually have a non-zero have non-defined values over land, and so if we were to interpolate these onto the model grid, it wouldn't be very good. So the next thing we're going to do is, before giving them as an output to this function, we're going to fill the NaN values. So the way to do that then is to do something like this. We're going to make a loop for I t equals 1 to the length of whatever the number of indices that we are loading. Okay, we're going to load one of these values at the time, so we're going to load indices of it. Okay, and the same is true here, it. Okay, and then once we load this, we're going to do an RNT fill of these two values. Okay, we're going to SSR equals RNT fill of SUSTR, comma. Actually, we have to provide the longitudes and latitudes, ij, and comma lat of I, comma j, then SUSTR, and then we're going to say a 3 by 3 degree decorrelation length scales. Okay, and we're going to do this for both the U and the V. V. Now these guys we can actually assign to the fork D array, which is going to be the output. So I'm going to call this fork D dot SUSTR, and this is going to be comma, comma, and this is going to be IT. Okay, so this is I'm assigning now these to the fork D array, which is going to be what our return output. Okay, and here. Okay. So with this in mind, now this actually is going to extract all this data. For cleanliness, I'm just going to indent this a little bit. Now because this is an automatic reallocation of the array with IT, every time you increase IT, it's going to reallocate this whole array. It's better if we actually define the size of this array ahead of time. So we're just going to say that this F12 is equal to zeros of length of I, comma, length of j, comma, length of indices. So I'm just going to define this array to have these dimensions. Okay, and the same is true for SV. Okay, then here I'm also going to say that fork d.lon is actually equal to lon of ij, which is the, and also the same is for latitude. This is going to be part of our return arguments, lat and xx, sorry, lat. Okay, so we've done that, and then I'm also going to add the mask here, fork ins, because the mask is also, the land mask is also return our output argument. So this is going to be ins mask. Okay, so now we have this as an output. So let's actually try to run this real quick. But before I do that, let me just check whether other fields that I need to initialize in fork D. I think that's I thought I had the fork array here. Whose that we were testing. I guess we cleared this. Okay, I think this is going to be, then we can execute this. So I'm going to execute this part of code here. I'm going to initialize the fork D array. MATLAB F12. So fork D. I have all these variables now, and I'm going to go back here, and we're going to execute this part here of script. And there was some problem here. Let's see. Oh, I didn't copy very well here. Let me copy well. 4. So I'm going to go here and just do that. And so now, if I do a pcolor, for example, of this array sustr, and fig. So this is the array that has the RNT fill. You see that it has been filled with values, and so we can actually look at the fork d.str, and so you see they look the same. So this has been filled, so it's very good. This actually didn't work well. I tell you why. Because if you remember, this sustr stuff is already filled in the land by the land values, but we want to replace those with an extrapolation of the ocean values. So what we need to do here then is ints. We have to multiply this by the mask r here, and also this one, so that it actually does fill in the the land values with ocean points. So this was a mistake that I made, and so we're going to redo this now. And you're going to see it's going to take a little bit longer because now it has to do the RNT fills. Okay, and now if we do mfig and we pcolor the fork D, you see that now it has extrapolated the values over land. Hold on, world coast. So it has extrapolated, and this looks different from the original land values, which is contained in this array here. You see it's very different. So we have replaced these land values, which would be extremely high and close to the coast, because of the different masking of the ecmwf data than it is for our ocean model. So you would have these big pixels here that would contaminate, but if we extrapolate the ocean values, then all of a sudden things look more smooth and everything looks better. Okay, so that's so we've done that, and so then the last step is we have to provide here as an output in fork D. We have to also give it the values, the time values of what this is for. So this fork D dot, let's say this is going to be year is equal to year, which we have. Then we have the month, and then I also like to carry the date num, and this is going to be, in this case, my date. Okay, so we are done here. So now we have a function that will produce a fork D for the ecmwf data, and we can try this right now as we speak. Here I'm just going to copy this function. I'm going to go in my MATLAB. I'm going to clear everything. I'm going to load the grid that we want to work with. I'm going to paste this. I'm going to extract date num 2001, comma, say the month of February now, and the date doesn't really count because these are monthly averages. And I'm going to extract it for grd.lonr, grd.letr. So we extract it. It's taking some time. I hope we didn't make any other mistake. Let's see why it's taking so long. Let's go back into our edit window. That's very strange, why it was taking so much time. Let's go back in the MATLAB window. Let's try one more time. So since it's not working, we're going to debug it again. This is the way this business works. So we do that, and then we let R, we do that, and now we're going to my date equals that. Okay, and let's go back into our edit window and let's debug this again. See what type of problem it went into. F12. So it's this mesh grid command that for some reason, oh, I see why. The problem with the mesh grid command is that probably inside this array I also had stored the longitudes and latitudes in a mesh grid. Yes, you see. And so now it's trying to remesh this grid. It's becoming a huge array, so that wasn't a problem. So what we're going to do then is we are going to, from this array, we only want to load mask. And so now probably this is going to work better. Oh, let's go in the MATLAB window. Sorry. Let's see if that was a problem. Yes. And so now we have extracted this, and we can now go back into our main forcing file. Here, vi main main nc files fork, and in the time dependent part, control forward. Here, instead of extracting the NCIP reanalysis, we can comment this out now. And we can extract the ecmwf wind stresses. So we're just going to go here and copy this function here. MATLAB, edit, F12. And we're going to put my date. In this case, it only extracts away the monthly means. And so now we can actually try this. I'm going to try it by hand here. We can load this. I'm going to clear everything in MATLAB. Okay, I'm going to select the grid. The only problem is that I have to do it N here. Okay, so now I have my grid loaded. Then I'm going to go here. I'm going to select the first part of the time-dependent forcing. So in this case, 1997 to 1998. So I'm just going to execute this part here and up to here. F12. Okay. And I'm going to go back here. And instead of executing the NCIP reanalysis, I'm going to execute the ecmwf data. MATLAB. And I'm just going to wait here. It could take some time because you're extracting these monthly values, but actually it didn't take too much time, fork D. So actually 24 values. That's great. We can even plot, for example, the monthly, the average over this period by just doing p color. And in this case, we have to use the fork D array because we don't have any more okay, and we can plot the mean, comma 2, comma 3, the mean of the third index. And we want to plot this and dot it with the mask. Okay, hold on, world coast. And that's the winds over the North Pacific, color bar. The units is something that we have to check in which units they had it. I didn't check that, and so that's something you may want to do. This has to be in newtons per meter square, and these obviously are not newtons per meter squares because winds typically go from 0.1. 1 Newton per meter square wind is a hell of a wind. So we'll have to convert these, but I'll leave this for you guys. And so then the next thing to do is to see whether we can use this function. Once we have the fork D, we could just use this RNT interp to actually place it on the grid. So we're going to just execute this last script here. And you can see that it's working like a charm, which is nice. And so now this netcdf file here contains, instead of the NCIP reanalysis, it contains the ecmwf data from 1997 to 1998. So just to summarize, then there are a couple of steps involved in this, and in creating this function here. And one is to extract the data, for the subgrid that that covers the model grid. Take the right dates, load the data. mask the data and use the RNT fill command to extrapolate the oceanic points into the rest of the grid, and then just complete this fork D array, structure array, to return as an output, and so then you have your fork D, and you can use the RNC interp function to place it on the grid. So that's a more elaborate example of how you can create your own forcing. And for the ecmwf case, of course, you remember you have to check the units, which I hadn't done. Okay, thank you.